earlier we talked about two ways of matching, one at the generator side, one at the load side, and where we left off on the load end is if you do a parallel match, one of the biggest issues is that you end up dissipating a lot of power in that parallel resistor that you put in to achieve matching on the load side. Right now we're going to conclude our select strategies by just looking at a few other creative ways to achieve matching, and then we'll wrap up this chapter by just doing a comparison of the pros and cons. So for the RC termination, it's basically a little riff on the parallel match situation where you have your Z0 coming out and you still have your parallel match resistor there and you have your load. But what you're going to do is you're actually going to stick a capacitor in between your matching resistor and the ground. And so let's take a look at what that does. When you're doing your selection, one of the things that you want to do is that to help fix the power issue, one of the key things you want is that if you call this C, and if you're calling that R your RC constant, it has to be much greater than that round trip T being the time it takes to make a one-way trip across this transmission line. So let's just take a look intuitively and see what happens if this criteria is met. So during your initial reflection, you have a sudden change. And remember, when you first turn something on and this capacitor is uncharged, what does it end up looking like? It ends up looking like a short. Right? So in the beginning, you're going to see just our parallel matching situation with that capacitor just being a short. And so then you successfully achieve a match. But however, so you're dissipating power, but while you're dissipating power, you end up charging up the capacitor. And so as T gets much greater than that charge up time, then your C becomes an open. And so now, towards the end, it's just going to look like this Z0 here. And then now you're going to have all the power going through the load resistor. And so by then it's okay because you've already worked through, there's already a situation where not much reflection is going on, and so everything is basically settled down, and so this isn't as big an issue. And so while you still have that same kind of power dissipation in the short term, once you reach that long-term situation, then you no longer have that power dissipation issue across the parallel impedance matching resistor. The other strategy that I'll introduce is called diode termination. So what that involves is that at your load, you hook up two diodes, where this side goes up to your upper rail, VCC. And actually that should be not Z0, that should just be your load, ZL. And so what that does is, let's just suppose this diode has a turn-on voltage of 0.7 volt. Then if you look at this circuit, what you're effectively doing is you're capping the load voltage to be between VCC plus 0.7 volts or minus 0.7 volts. And remember, VL is going to be equal to V plus V minus. So what this does is you're still poorly matched if you weren't well matched to begin with. But because this diode, once you exceed this range, one of these diodes would turn on and the voltage would get capped. And so what you're doing is you're limiting the size of the reflection. So let's just do a short example just to put some numbers to it. So let's just say this is 50 ohms, and then you're going into a 50 ohm line, and then you have your little diode set up here. And you have your load, and let's just say the load is, again, 2000. That really poor situation there. So let's just say the generator is 10 volts, then the input voltage is going to be the voltage divider between this 50 and this 50 times 10. So Z0 over Z0 plus ZG, which is going to be 5 volts going in. And then your gamma at the load side was that poor match that we had in the earlier example. So 2000 minus 50 over 2000 plus 50 is going to be 0.951. So your V plus going in, which is equal to V in, is going to be 5 volts, and your V minus is going to be 4.756 volts. So your V load, which is equal to V plus plus V minus, is going to be equal to 9.756. But because that's greater than VCC plus 0.7, the diode is going to limit it to 5.7 volts. And so what that means is that in your diagram, you have 5 volts coming this way, but because the V load, which is the sum of the incoming wave and the reflected wave, is capped out at 5.7 volts, your reflected wave is now limited at 0.7. And then any extra reflected wave gets passed through the diode. So again, this doesn't solve the reflection, but depending on what you have on the load side, you might continually have these little reflections bouncing off, but it's another way to get there.